Okay, so let's look at question 9. We need to use a Maxwell relation to show that the change in entropy of a van der Waals gas is linearly dependent on the volume of the gas. So basically, we need to show that some function y is equal to something like this, so that we can say y is linearly dependent on x, for example, but in this case, we need to show that the entropy, the change in entropy is linearly dependent on the volume, and exactly in that form. So if we look at the Maxwell relations, the one that pops out for the change in entropy with change in volume is actually this one. So that's the one that we will use. And if we were go smartly about this, the only one that we can really use to relate it to equations of state is one that looks like this. It's actually one that we've used before as well. So in other words, because equations of state are normally written in terms with pressure as the subject, so in other words, P equals something, right? So then we can relate the equation of state of the van der Waals gas to the entropy change with the volume. Okay, so that means we just need to write the equation of state of the van der Waals gas, which is nRT over V minus NB minus A n squared over V squared. Right. So then we plug it in here. We go d dt of nRT over V minus NB minus A n squared over V squared at constant volume. So this first one, we take out all the parts that does nothing to do with V with T, so this is all constant. So we can say that just remains constant, so that's nR over V minus NB, and then dt is 1. That's a constant, so that's 0. So that gives us the derivative of that. Alright. So having that, let's write this down here. We then have that ds to dv at constant temperature is equal to nr over v minus nb. Okay. But we want delta s, not ds over dv. We want to calculate delta s. So what I'm going to do now is we can switch between ds and ds. So what I'm going to do is I'm going to multiply by dv throughout to get ds on both sides. So the ds on this side, and then so I'm changing from the partial derivatives to the formal derivatives, so then I can drop the t here. It's like a rap song. I'm going to drop the t here. Okay, anyway, then we have that, and then I'm going to integrate. So I'm going to integrate this between the initial entropy and the final entropy, and I'm just going to integrate this generally. Yeah. Okay. So this then becomes delta S, more written out nice explicitly, SF minus SI is equal to delta S is equal to this integral here is nr, the integral of 1 over v minus nb dv, which is equal to nr. So this is the general integral, so then we end up with ln v minus nb. I'm doing the absolute value thing again. And because we just had a general integral, we need to remember there's some constant. Let's just call it constant 1 that we have. Okay. So this makes sense because the derivative of this would be nr times 1 over this derivative of that would just be 1. So that's all cool. Constant would fall away. Then we have delta S. Right. And then if we just give these things names, so in other words, we just let, so then we say let nr equal beta and c1 equal alpha, then delta S is equal to alpha plus beta ln of v minus nb, which is exactly what we had to prove. So in other words, the entropy, the change in entropy of a van der Waals gas depends linearly on the volume of that gas. Right, and so you can actually do that. It's quite a simple thing. You can do this for a perfect gas, and you'll see it actually depends on solely on the volume or ln of the volume, without the interaction constant, of course, because there's nothing like that for the perfect gas. Very nice question. Very cute question. I like these types of questions. No calculations involved. Yeah. Okay, so I don't think there's anything too challenging on this. Interpretation-wise, what does this mean? Means if the entropy changes linearly with the volume, just depending on the volume minus this factor. So it means the repulsive forces does have some sort of effect on that, but it is a linear change. So the disorder is dependent on the volume, essentially. So, which makes sense. I mean, if the volume increases, the disorder will increase. So the world still goes around. Makes sense at the end of the day. If you're going to increase the volume of a gas, it will become more orderly. And if you decrease the volume of that same gas, it will become less disorderly. In other words, more orderly. So just the short interpretation. Always, I think I've been interpreting everything along the way, but always think what you're calculating, what you're doing. Like, why do you actually do these things? You're not just doing them to pass a degree, you're actually doing them to try and make sense of what you're doing. All right.